last course is dedicated to a fatigue model that we describe a fatigue sample that provides a random model for the SN curves that give the lifetime n as a function of the stress range S. This is the model. It is a random model which depends on 5 parameters, n0, delta sigma 0, delta, lambda, and beta, but we consider the random. We explain how to simulate any given cumulative distribution functions, because in OpenBox we can simulate only a few distributions. One interesting trick to simulate a given cumulative distribution function is to simulate a Poisson distribution with null observations and choosing the Poisson parameter to have identical likelihood for the Poisson and the simulated models. The Poisson Px of theta and the zero observation P of 0 theta likelihoods are the ones in the first equations. If we make theta equal to 0, you get the P0 phi, which is e to the minus phi. If we want to simulate a Weibull model which has the cumulative distribution given there, f capital F, and the density function lowercase f, what we need to do is just to equate the density of this Weibull distribution with the P0 phi density above. If we make both equal and we take logs, we get that phi should be equal to minus log of this expression that is below. Just including this equation in the model, we simulate the Weibull distribution, but we use a fictitious or virtual Poisson model with 0 observations. So that in the model commands here, you can see that in the fourth line, you have phi of I, and then you have the expression that corresponds to the equation in the previous transparency in the lower part. So this is the way of simulating the Weibull distribution, and you can do the same for any other distribution that is not included in the OpenBook software. Unfortunately, the OpenBook software have included as default only a few distributions, so that this is a very interesting aid to simulate any distribution. The model commands is completed with the priors for n0, delta 0, beta, lambda, and delta. We use uniform densities with given bounds. In order to fix these bounds, we have used the standard random model, which is not a Bayesian model. When the parameters are assumed to be random, we have the Bayesian model, so that we use as a starting item of information to define the priors, the result that we obtain with the random model, but not Bayesian model. This is the result of the Doodle model. Look, that it is a very nice Bayesian network that reflects very well what are the variables, which includes real variables and artificial variables, which are the parameters, and we have the relation among the different parameters. This is the commands that you can obtain from the previous plot if you use the prettyprint option in the menus, and then when you have that, you can start to use the OpenBooks by compiling the commands and the model as we have mentioned before. And then you get the estimation of the different parameters using density functions. In this transparency, you can see the initial percentile using classical methods based on maximum likelihood, that is not Bayesian methods. These are the same percentiles, but for the median percentiles. And this is finally the model with all the percentiles of the percentiles, which is a nice contribution that it is not well used before. You can use the MATLAB to write automatically the scripts necessary to run this model, so that you just need to execute the script and all the thing will be automatically done, and you save a lot of time. And this is a plot, a 0-1 normalized values of the sample plot to see the relation between the different variables. We have used this also to the Holman data, which is another example, and these are the results of the posterior densities for the Holman data. These are the densities that you obtain for the different parameters. These are the percentiles corresponding to the classical methods. These are the median percentiles for the Bayesian approach, and these are the complete percentiles of the percentiles for the Holman data. You can see that the fit of the model to data to the model is very good. And this is the end of this lesson dedicated to a fatigue problem. This is an example of a stochastic process that suggests interesting applications. If you want to know new application of stochastic processes and learn how to use families of distributions not implementing in open bugs, you should incorporate models as those explained in this lesson. We strongly recommend the reader to see the MATLAB codes to call open bugs for this and other examples, which are included as complementary course materials.